Okay, good morning. It looks like there's not too many students here today, which might be beneficial. So, Julie, Jennifer, Jocelyn, Lydia, I'm going to ask that you participate with me um, on the following theorem. So that means I'd like it if you spoke up or sent something in chat so I can see it. I want to walk through this proof or walk through the proof process with a theorem on prime numbers or composites in prime numbers. Okay, so the theorem states that if n is a positive composite actually, we don't need positive. Just say n is a composite integer. Make sure I'm stating it right. Yep. Composite integer. Then n has a prime factor less than or equal to square root of n. Prime factor, divisor, same thing. Okay, so pretend we're looking at this as students. Okay, so when coming up with your scratch word here, I know it's typical to choose a proof method and then kind of go with that method. But when you're kind of blind, as you might be with this theorem here, what would be the first things you would start to do, like when looking at this? Like, what is the very first thing that you would maybe write over here as your scratch word?
That n is a composite integer.
Good. That's exactly where I would start. So I would just say, okay, what does that mean to be a composite? N is a composite.
Would it mean that that n is like multiplied to be from two numbers or so?
Really close. You're thinking the right way. But so if you look at the formal definition of being a prime, right? A prime is a number whose only divisors are one in itself and greater than it. So a prime number is a positive integer greater than one whose only divisors are one in itself. If it's not prime, then it's called composite, which means that it has some divisors other than itself, right? So one way that you can look at this is say, well, this means that n is not prime. Right? If it's composite, it's not prime. And if it's not prime, it means that n has divisors other than one in itself. So that's saying something. Right? Like that we have some information if we assume the hypothesis there. Okay. So maybe, so okay, now that we've made it this far, maybe we can use this to introduce some variables or something like this. Like, so what would be the next step? Like in your scratchbook, what do you think that you would write next?
Would it be that n has a prime factor? Basically, the next question or the next statement, which is n has a prime factor less than or equal to n squared.
So that's what we're trying to show. We're not there yet. We just know that it's not prime, so we know that n has divisors. That's all we have from this right here. But as we've done before in the past, when we use a definition, right, it's often the case that we have this sentence that means like a sentence, and then the immediate step after that is to introduce some variables to kind of work with algebraically, right? Like this has kind of been a pattern that we've had with the simple proofs that y'all have been doing. So if n is not prime, it has divisors other than itself. So what do you think the next, like take another guess at what the next step would be? The idea is to introduce some variables somehow.
Would we be basically proving that n has divisors other than one in itself? Would we like start using numbers with that?
And maybe not numbers, but maybe some variables to represent those divisors, right? So, for example, this is the scratch word, so maybe we could say something like, so, maybe like take a letter, I don't know, A be a divisor of n, A divides n, right? So let A be a divisor of n, where I don't know, if A is a divisor of n, then A is equal, I mean, n is equal to A times some integer c, right? So if n has divisors other than one in itself, then there is some divisor, I'm going to call it A, you can call it whatever you want, I chose A. It divides n, where A is not equal to 1 or n, and if A divides n, then by definition, n is equal to A times some integer c. And A and C are integers, or something like that. So notice what we did. We assumed something, and then it gives us a definition. And then once we have a definition, we typically like to write something with some type of like maybe equations or another definition. We're trying to get to some information that we can manipulate algebraically. So, okay. So here, if it's not prime, then it has divisors other than one in itself. Okay. So we know that there is some divisor, call it A, right? That divides n. It's where A is not equal to n or 1. And we know that n is equal to A times some integer c if A divides it. Okay. So now we need to look. So we've kind of extracted all the information that we could out of the hypothesis, assuming that n is a composite. Okay. So that's that business there. Now, in previous lectures, I've mentioned that if you don't know where you're at and you're kind of stuck, what technique have I suggested to get unstuck, just to kind of gather the most information? So what proof technique gives you the most information to work with? I've mentioned this before in a few lectures. You can guess too, it's fine, you just want to guess. And this is just a personal preference of mine when looking at proofs. If I get stuck, I proceed by way of block. Anybody? Just guess. There's only like a few options.
Putting values into the second statement that we put for our scratch work?
Well, that would be a specific instance of like trying to like learn more about why it might be true. But I'm talking more of like a proof technique. And what I was trying to get at is that like when I get lost, I kind of assume by way of contradiction. To get a sense, because when you assume by way of contradiction, you assume the hypothesis, which we've already done. I don't really know where to go with it from there because I'm looking at the conclusion, I don't know. So I have my hypothesis, and if by contradiction you assume the hypothesis and not the conclusion, then okay, what happens after you make that assumption? Right? Assuming not the conclusion gives you more stuff to work with. So what happens here, okay, so here we're gonna kind of like insert a contradiction test in a sense. So what happens, so these A and C are clearly factors of N, right? So we don't know if A is prime, we don't know if C is prime, but let's just say, okay, what happens if neither one of those is less than or equal to the square root of N? So what happens if we assume that A is strictly greater than root N? So what if we assume this? So if I was looking at this proof and I say, okay, N has a prime factor less than or equal to N, I see that I have factors there. They're not, I don't know if they're prime, I just know they're factors, right? Then, like, what happens if both of those happen to be greater than root N?
Then N wouldn't be composite?
I think you're on the right track. Okay, so these are both, so square root of N is positive, square root of N is positive, so A is positive, C is positive. So what happens if I multiply A times C? Well,
N is equal to N.
Right, exactly. N is equal to A times C, but A is greater than the root of N, right? And C is also greater than the root of N. So A times C is strictly greater than root N times root N, but what is this product equal to? Root N times root N is just
N.
There is the contradiction. N is equal to that, but that's strictly greater than N. So what this means is that that can't be true. So A is either less than or equal to the root N, or C is less than or equal to root N. So this right here can't happen. So it means that this must be true. So if A is less than or equal to root n, then or C is less than or equal to root n, and one of these is either prime or has prime factors, we know that there's a prime factor less than or equal to root n. So each of A and C, they have prime factors or they're prime. So since that or that, we know that there is at least one prime less than or equal to the root n, which happens to also be a factor of n. So putting this all together, we can say something like, maybe like let n be a composite integer okay. So then n has a factor, or yeah, or a divisor, as a divisor. I'll call it the divisor B instead of A, just because I have my little A there. It looks like it's the divisor B. Um, and then maybe so that n is equal to B times C, and B and C are integers. Something like that. So we assume that n is a composite integer, then n has a factor b, so that n is equal to b times c, where b and c are integers. Okay, so and that pretty much knocks out that bullet point and that bullet point, and now we move to this contradiction criteria. So the way that you can throw in contradictions in the middle of the proof. So notice, typically when we've written proof by contradiction, we say at the very beginning, by way of contradiction, stuff. If you're going to throw in contradiction in the middle of the proof, you can say something like, see how I have a question mark right there? That's kind of like, well, what happens if that is the case? So you can say something like, this would be change that to B. So if B is strictly greater than root n, and C is strictly greater than root n, then B times C is strictly greater than root n times root n, which is equal to n, a contradiction. So a lot of times when you're writing proofs and you realize that there can be a contradiction in the middle, you pose a question or like a conditional. So if that and that, then that, which is a contradiction, since n is equal to b times c. And maybe even write that a contradiction since n is equal to b times c. So then you can say, therefore, the opposite of this if statement must hold. So therefore, B is less than or equal to root n, or C is less than or equal to root n. Now, I didn't write it here, but maybe we can make this very clear. So either that holds or that holds. It won't matter in the end. So that's where I'm going to use this without loss of generality. Just assume that one. Okay? Because at least one of those has to hold. So without loss of generality. Suppose B is less than or equal to root n. It won't matter which one in the end. It's just I'm choosing that one. Okay, so then we can say since B is either prime or has prime factors, which would also be factors of n. Any factor of B is also going to be a factor of n. We are done. So here, so B is either prime. If B is prime, then that's a prime factor of n less than or equal to the square root of n. And if B wasn't prime, then B has prime factors, which would also be factors of n, which means that n has a prime factor less than or equal to B, which is less than or equal to square root of n. So what all of you probably need to do with these proofs that are getting a little bit more involved is, so like the way that I would study these when I was an undergraduate, and even in graduate school when I was learning difficult proofs, I would write down the proof exactly as I have, like your instructor, right? And then I would try to understand each line, and then I would get a new sheet of paper, write the theorem down, and then try to build the scratch work, and then try to write the proof, and then compare it to what my instructor wrote. And then I would iterate this a few times, like probably 4 or 5 times on a given one proof, write it over 4 or 5 times, always trying to get it done on your own, like keep your notes away from you and have only your pen and paper in front of you. Try to piece it together without referring back to what I've done. And then after you finish it, then compare to what I showed you in class. Okay? All right. So that is an important result, actually, because it gives a brute force approach to determine the prime factors of a given number, right? Or determine if a number is indeed prime. So because if it's composite, then it has a prime factor less than or equal to root n. So if I give you a number and you want to check if it's prime, you just have to check all the divisors up to root n instead of going all the way up to n itself. Okay, so what's next? Oh, so another definition. So let A and B be integers. We can just say positive for now. Both non-zero. I'm not going to say let A and B be integers, both non-zero. The largest integer D such that D divides A and D divides B is called the greatest common divisor of A and B. Okay. And this is written GCD of AB. Okay. All right, so it's the definition. I should probably elaborate on this a little bit more. So if the GCD of A and B is equal to 1, then A and B are called relatively prime. All right, so it's kind of like two definitions in there. Okay, so I guess just an example of how these things work. So GCD of say 14 and 36 would be 12. And then maybe GCD of, I don't know, 8 and 15 would be 1. So 8 and 15 are relatively prime because their GCD is 1. 14 and 36 not relatively prime, the GCD is 12. Okay, so we can express the GCD of two integers in terms of their prime factorizations. So if you recall, every positive integer greater than 1 has a unique prime factorization. So suppose that A is equal to P1 to the power of A1 times P2 to the power A2 times dot 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 Pn to the power of An. So each of those P's, so this is a prime factorization of A. And then suppose B is equal to P1 to the power B1 times P2 to the power of B2 times dot 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 Pn to the power of Bn. That's also a prime factorization. Then if you have the prime factorizations of A and B, the GCD of A and B has a closed formula. So this would be P1 to the power min of A1 and B1 times P2 to the power min of A2 comma B2 times dot 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 times Pn to the power min of An Bn. Okay, so this looks kind of wonky, I'm assuming to you. Maybe we can look at the GCD of 14 and 36. So, 14 is equal to 2 times 7, right? That's its unique prime factorization. And then 36 is equal to 6 times 6, but that's equal to 2 times 3 times 2 times 3, which is equal to 2 to the power 2 times 3 to the power 2. Okay, so if we wanted to use this formula on the GCD of these two things, so it looks like, so 2 to the power 1, 7 to the power 1. So if I write out all the primes that are included in both of these factorizations, 14 is equal to 2 to the power 1 times 3 to the power 0 times 7 to the power 1. And 36 is equal to 2 to the power 2 times 3 to the power 2 times 7 to the power 0. So this is a prime factorization of 36, the prime factorization of 14. So the GCD of 14 and 36 is going to be equal to, so the power of 2 here is 1, the power of 2 here is 2. So 2, the min of those values is 1. So the GCD of 14 and 36 to be 2 to the power 1 times, then we have 3 to the power 0, 3 to the power 2, so the minimum of 0, 2, 0, so times 3 to the power 0. Did I miss something here? 4, okay, just keep on going. And then 1 and 0, so times 7. Everybody down right? Min? Kind of rushing it. Huh. Because this is not going to work, right? The greatest common, oh, what am I doing here? The greatest common divisor is 2. 12 doesn't divide 14. Yeah. So here we get 2 to the power 1 times 3 to the power 0 times 7 to the power 0. So 2. I don't know why I wrote a 12 there. But yeah, so if you have the prime factorization of your two numbers A and B, then according to this formula, you can find the GCD. You just take the prime factorizations, and then you take the minimum power of each prime, and then you raise the primes to that min power, multiply them together, and you get GCD. Okay, so continue. That's the GCD. Okay, so the next definition is related. Say the least common multiple. The least common multiple of A and B that are positive integers is the smallest positive integer D, I suppose. Yeah, D is a positive integer such that A divides D and E divides D. And this is written LCM of AB. Okay, this is the least common multiple. Okay, so using the notation that I just wrote for the prime factorizations, you can just observe that least common multiple of integers A and B is equal to E1 to the max now of A1, B1 times E2 times the max exponent for that prime factor. That's A2, B2 times dot, dot, dot. And then your in prime factor to the maximum exponent out of A and B. So as a consequence of this formula and the formula for GCD, we get this theorem that so if A and B are positive integers, then A times B is equal to the GCD of A times B times the LCM. And for the proof, I want you to try it. You have a formula, you have another formula, you just have to piece them together and kind of argue why you get A times B when you take the GCD times the LCM. Okay. All right. So you try that. Now, the next result that I'm going to write down is going to take up more space than I have right here. So I'm going to go ahead and erase this and start over from the top. Okay, so before writing down this result, I just want to recall that the following, I'll call it lemma, A or something. Okay, so in this lemma states that if A divides B and A divides C, then A divides B minus Now, technically, we should prove that, but it's so similar to the proof that I gave in the first day of number theory that I'll let you prove this one as well. So you prove this. But we're going to use this lemma, which a lemma is a theorem that's used as a tool to prove another result. So we're going to say, we're going to use this lemma to prove another lemma. I'll call this like lemma B or something. And this lemma states that, so if A, B, Q, and R are integers with A equals to, say, B times Q plus R, then the GCD of A and B is equal to the GCD of B and R. Okay? So this is interesting, right? So you might not realize it yet, but it will turn out to be interesting. That you have A and B, right? And A can be expressed as this linear combination of integers here. Then the GCD of A and B is the same thing as the GCD of B and R. Where R is the remainder and B is the divisor of A. Okay? So let's look at the proof here. Okay, so I'm going to ask for more participation from you guys. This proof is not as difficult as you might think it would be. I'll give you a hint. I'll say that show any say any divisor of A and B is also a divisor of B and R. And vice versa. So why would this be useful? And like, this is another thing that a lot of you are going to have to get used to as you take your upper level math courses. You're going to receive hints, right? You're going to receive hints that your professor definitely gives to you for a reason. And this would be a good hint on here. Well, if you think about it, right? If you look at all of the divisors of A and B, there is a biggest one. It's the GCD, right? Of A and B. Now, if every divisor of A and B is also a divisor of B and R, then the GCD of this is less than or equal to the GCD of B and R. Does that make sense? Right? So, okay. I have a feeling that you're not and like this isn't so clear. So maybe I need more scratch work. Just a little bit more. So maybe like note that the GCD of A and B less than or equal to the GCD of B and R, and the GCD of AB greater than or equal to the GCD of B, R imply that they're equal. Does that make sense? Like, this is not even like relative to like a proof course. This is just in general a number, right? So like if x is less than or equal to y and x is greater than or equal to y, then x must equal y, right? That's clear. If that and that, then they have to be equal. Does that make sense? Somebody. Somebody's got to say whether or not this makes sense. Right here.
Just a little hard to visualize it, but I somewhat get it, but I guess with more practice, I guess I could.
Okay, good. You spoke up about that, right? That's what you're talking about?
Yeah.
Okay, so x less than or equal to what? Right, so x is at most y, and just suppose that that holds, right? So if that happens, and also y is less than or equal, so maybe, okay, so x less than or equal to y, and x is also greater than or equal to y, it means, so this implies, right, x must equal y. Think about it, like, if it's less than or equal to and it's greater than or equal to, the only option is for it to equal. Like let's maybe, can I do this algebraically?
It makes sense. Now that you explained it a little more.
Yeah, so it's yeah, it's almost, I'm trying to think of the best way to describe it other than just saying like, okay, maybe this, like, like, if they didn't equal, right? If they didn't equal for some reason, and that held and that held, then that means that x must have been less than y, because x is less than or equal, but you assume that it doesn't. But then from this one, x must have been greater than y, because you assume that it doesn't equal. And that right there, that's a contradiction. You can't be less than and greater than. So it must be the case that that assumption is wrong and that they equal. So if that and that, then they must equal. So that's all I'm like, that's an important thing to note just in general. This comes up quite a bit in math classes where you want to show an equation, and the way that you do that is by showing less than or equal to and greater than or equal to. So we want to show this equation here. That the GCD of A and B is equal to the GCD of B and R. So maybe if I actually write out the proof and then go through the scratch course that would have led up to it, that might help you understand. So, okay. So maybe something like first, I'm gonna have to erase all that business over there to make this in one go. Okay, so first we show that the GCD of A and B is at most the GCD of B and O. Okay, so in order to do this, okay, so we can say something like, suppose D is a divisor of A and B. I.e. D, yeah, the divisor of A and B. I.e. D divides A and D divides B. Okay. So D is just an arbitrary divisor of A and B, right? So we're assuming that A is equal to B times C plus R. So we'll be like hence, and then maybe therefore, if D divides A and D divides B, then D divides A minus B times Q, which is equal to R, by lemma A. Okay, let's like stop here. So first we want to show, this. We're just letting the reader know that that's what we want them to see. That's what we want to describe to the reader. So suppose D is an integer, is a divisor of A and B. So D divides A and D divides B. Therefore, D divides A minus B times Q. Because lemma A states that if A divides this, A divides that, then A divides the difference. So if D divides that, and D divides that, which it does, because it divides B, it divides A minus them, which is equal to R. And we're just using this lemma up here. Okay, so then, so D also divides, since that's equal to R, right, the difference is equal to R, so hence D divides B and D divides R because it divides that difference. And we're assuming that, so A minus that is equal to R. So what does that mean? It means that if there's something that divides both A and B, it must also divide B and R. Okay? So then we can say, since any divisor of A and B will divide B and R. The GCD of A and B will divide B and R. Right, so what did we show? We showed that if we pick an arbitrary divisor of A and B, so then they call it D. If any arbitrary divisor of A and B will also divide R. So that arbitrary divisor will divide B and R. So that was an arbitrary divisor. It was any one of them, right? So since any divisor of A and B will divide B and R, the GCD, which is a divisor, will also divide B and R. So hence, it follows that the GCD of A and B is at most the GCD of B and R. Maybe you can't read that too well. Follows that GCD of A and B is at most the GCD of B and R. Now, I'm almost positive that that's kind of, it's not so clear to some of you. Okay, so ignoring the proof that any divisor of A and B will divide B and R, which is up to this period right here, right there, I want one of you to explain to me this implication right here. So, someone has to explain that to me. So since any divisor of A and B will divide B and R, the GCD of A and B will divide B and R. It follows that inequality. Why does that follow? Why is it at most the GCD of B and R? I'm going to get it out of one of you somehow. All right. So let, this is not a part of the proof. I'm just trying to get one of you to explain this inequality to me. So, okay, so let D1, D2, dot, 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 Dn. So maybe I'll use So let these be the divisors of A and B. Each one of these is a divisor of A and B, right? So each one of these is so these are the divisors of A and B. Okay? In their order of an increasing order. So this is like the largest divisor, which is the greatest common divisor of A and B. Okay? So that's the largest one, that's the smallest one, that's 1, right? So, okay. Now, so now let like C1, C2, CM, call it, be the GCD of B and R. Okay. So C1, C2 up to CM. So those are like these are the common divisors of B and R. Okay. Somebody help me out here. Any divisors of A and B will divide B and R. Okay? These are all of the divisors of A and B. These are all of them. All the possible divisors of A and B. And these are the divisors of D and R. Okay? Divisors of A and B, divisors of B and R. Okay? Any divisor of A and B will divide B and R. These are divisors of A and B. Are these numbers also over here?
You're suggesting that the largest 1dn would be in the divisors of BNR, but it can't be the largest.
You're so close. You're so close. Any of these numbers in this list, right? Because I just picked an arbitrary divisor here, right? Any divisor of A and B, and these are all of the divisors of A and B. Any of those will also divide B and R. So what that means is that every single one of these divisors here also divides B and R. So they're going to be over here as well. Every single one of these will be over here. Does that make sense?
It does, but what I'm confused about is if you can say that, couldn't you say the opposite as well?
Not yet. We're getting there, and that's the second part of the proof, really. All we've shown is that if we pick a divisor of A and B, it's also a divisor of B and R. That's all we've shown. Which means that all of these appear over here. Which means that technically all we know is that somewhere in here, and we have no idea where, somewhere in this list is the N. Somewhere. We just know that it's in that list somewhere. Where is it? Who knows? We just know that Dn, which is a divisor of AB, which is the GCD, must also be a divisor of B and R. So it's somewhere in here, but we don't know where. That question mark, this, because we have no idea where it is in the list, is why we have to write the inequality. We have no idea where it is. It could be the last one, but it could be the second one. Who knows, right? We just know that it's in that list somewhere, which means that this is like Dn, right? Dn is that thing, the GCD. We just know that it's over there somewhere. So we know that it's at most, it's less than or equal to the GCD of B and R. But as of right now, we have no idea where it's at. We just know that it's somewhere in here. Over there? I don't know. Is it that one? I don't know. Where is it? I don't know. I just know that everything over here is over here because that's what we argued. And this one, which is the biggest one, is over here somewhere. So we know that it's less than or equal to the biggest number over there. Is that?
It makes sense now. So then on the second part, we would prove the opposite. And from there, we can assume that they're both equal since they're neither greater or less than?
Exactly.
Okay.
Exactly. So all we've done, let's say the best way to is you did a good job of explaining it. We showed this is break it back down step by step. We pick an arbitrary divisor of A and B, and that divisor must divide R. So if it divides A and B, then it also divides B and R. So any divisor of A and B will divide B and R. The GCD of A and B happens to be one of those. So if you look at all of the divisors of B and R, the GCD of A and B is somewhere over here. We don't know where it's at. We just know that it's in that list, so it's less than or equal to the biggest number in the list, which happens to be the GCD of B and R. So that's where we write that inequality. So what we've done is we've established, with this piece here, we've established that, so we know the GCD of A and B is at most the GCD of B and R. We have got that down. And the way that we did that is we showed that any divisor of A and B must also be a divisor of B and R. So the biggest divisor of A and B is at most the biggest divisor of B and R. That's the best way to describe it. All of this business is doing exactly that. So I'll state it one more time for clarity. What we've shown is that any divisor of A and B is also a divisor of B and R. So the largest divisor of A and B is at most the size of the largest divisor of B and R. That's what this proof has shown here. Now it's time to do the rest of it. So next, we show that the GCD of A and B is greater than or equal to the GCD of B and R. Okay. Okay, so this is not so bad again. So suppose D is some integer with D dividing B and D dividing R. So suppose D is a divisor of B and R, as let's say. Okay? Then since D divides B and D divides R, D divides B times Q plus R. That's like another version of this limit. It divides the two parts and it divides the difference and it also divides the sum. But what is BQ plus R? That's equal to A. So D divides B and D divides A. So in a similar fashion, we've kind of gone in reverse. Hence, any divisor of B and R is also a divisor of A and B. So maybe I'll write it out with words this time, make it a little more clear. Maybe say, since the GCD of B and R is a divisor of B and R, the GCD of B and R is also a divisor of A and B. So that is a divisor of A and B, hence the GCD of A and B, which is the largest among all possible divisors of A and B, is greater than or equal to the GCD of B and R. So that's the largest divisor of A and B. That must be some divisor of A and B, so that's at most the largest one. And then you would finally finish off the proof by saying since the GCD of A and B is less than or equal to the GCD of B and R, and the GCD of A and B is greater than or equal to the GCD of B and R, it follows that they equal. So the proof in Rosen of this result is much shorter, but I don't think that it explains as much. So basically, the idea behind the proof was that so if A is equal to this linear combination here, right? Then all of the divisors of both A and B are the same as all of the divisors of both B and R. They must be the same. We just proved it. And what that implies as a consequence is that the GCD of A and B is equal to the GCD of B and R. Okay. So I'm not like completely satisfied with this proof, but I guess it did illustrate to me something that some of you might be missing, is that it's almost like a subset argument. Like the subset of divisors of the set of divisors of A and B is a subset of the divisors of B and R. That's where that inequality comes from, because they have a maximum. And then the same goes with B and R divisors being a subset of the divisors of A and B. So I'm gonna try to think of a better way to prove it, but hopefully you gain some insight about getting these upper and lower bounds, and then also knowing to prove an equation, you can always prove less than or equal to and greater than or equal to, which implies the equality. Okay, so if you've been following along with Rosen, I would say I don't see any good problems to work on here, but I would definitely read. So this is in Rosen section 3.4. No, 4.3. I would definitely read that section. All right, so that'll be it for today. Please make it to class on Thursday so I can ask more questions and try to get a sense of where everyone's at in class so I can be sure to adjust my exam and how I write it for exam 2 accordingly. So please try to make it on Thursday. Okay, everyone stay safe, and I will see everyone then.
Thank you, Professor. Have a good day.
You too.